Coming up, a hands-on beer garden physics lab test in a proper engineering R&D facility supported by actual engineering calculations. Yes! What a dangerous precedent to set. But I know, like you, I'm getting aroused just thinking about it. The definitive guide to engine fuel consumption at idle is next. I'm John Cadogan from AutoExpert.com.au, the place where Australian new car buyers save thousands off their next new cars. Hit me up on the website for that. Also in this report, of course, we will out-troll several A-grade nuts and crack the kooky code of both volumetric efficiency and manifold vacuum. And I will show you the neatest mathematical hack of all time for dimensional analysis. And I assure you, this report will be awarded Total Nerd Certification before you get to the end of this video. Yes! But the mathematics is actually quite severe. This video is therefore rated PBA for probable brain aneurysm. So do not come crying to me by friggin' Ouija board if you suffer a stroke before we get to the very end. It's not my problem. Now, I loves me a good controversy as much as the next dude or dudette, although frankly, I'm actually quite pleased I'm not a dudette, because if I were, I would most probably not be able to leave my breasts alone, and that would, tragically enough, deprive the universe of videos such as these. Nobody wants that. Many of you actually continue to allege that I am wrong about engine fuel consumption at idle. Regarding a previous vid, a car uses 0.6 litres of fuel per hour per litre of displacement. At least this is what that guy on the workshop says. P.S. Sorry about dispel lung. That's actually somewhat creative. You'd have to actually know how to spell those words to do that. So, bonus points for literacy there. Now, I'm pretty sure it's 600 millilitres per hour ballpark for a 2-litre engine at idle under zero load. There is no per litre about it. That's a friggin' myth. But many people continue to tell me it's 600 per hour per litre of displacement. So let us critically assess that today. Some people even send me messages to this effect in English. The estimated fuel consumption of an idling engine is 0.6 litres per hour per litre of engine displacement. No need to shout, Jeanette. I heard you the first time, mate. Physical test in just a few minutes. Let's get this sorted one way or the other. But first, let us go now to a Brexit Stanny Nobel Prize winner via his award-winning YouTube channel, The Workshop, as previously alerted. Presumably he called it The Workshop because retard in a badly lit garage was already taken.
Oh my god, if you are going to do that, get it fucking right. Because I'm sorry, John, but you're the fucking idiot in all of this. And then he says, the average 2-litre car consumes 1.6 litres of fuel at idle. At idle. There we go. Right. So, dude, I was like, that's wrong. You're the fucking idiot. Because if you actually read it, instead of skim reading it, it says 0.6 litres of fuel at idle in 1 hour per litre. As in a 1000cc engine. You specifically say a 2-litre engine. Well, that would be 1.2 litres, fuck nut. You can't even read. Oh yes! You didn't do any calculations, you just ran out there, quickly typed it, all full of yourself, read that, missed the important bit, and then you've just gone and made a complete fuck up.
if engineering taught me anything, okay, it's that the facts really don't care what you think about them, and if you want to get something right, you need to adapt to the facts and not the other way around. Adapting the facts to suit your worldview is a fool's errand and at times a complete recipe for disaster. So here's what the facts suggest about a modern 2-litre engine at idle. Let's take a 2-litre 4-cylinder petrol 4-stroke, so a conventional engine idling at some conventional speed like 600 RPM just to make the mental arithmetic easy, because I don't want you to bleed from the ears yet. That's later. So the first piece of mental arithmetic is that's 300 strokes per minute, because there's 1 stroke for every 2 revolutions, because it's a 4-stroke engine. Suck, squeeze, bang and blow. And that takes 2 revs, right? So the engine should ideally, if the world were ideal, it would suck in 300 strokes times 2 litres is 600 litres per minute of air. But as I hope you've realised by now, the world really isn't that ideal, and there's a couple of impediments to the engine idling. And the first one is the throttle, which is closed. So imagine you're snorkeling in the Caribbean or something. You've got your face in the ocean, you're looking at fish, whatever, chicks in bikinis probably, and all of a sudden somebody slams the throttle shut in your snorkel just as you're trying to breathe in. This is exactly how it is for the engine. You'd have to suck pretty hard to keep yourself going, and so does the engine, right? It leads to this phenomenon called manifold vacuum, which I'm sure you've heard about, which is just that the pressure in the manifold is lower than atmospheric pressure, and it's a lot lower at idle because the throttle is shut and there's a lot of sucking going on. It's typically about 1/3 of an atmosphere, so about 1/3 of the density of air that you're used to sucking into your lungs. And that reduces your 600 ideal litres per minute to about 200 litres per minute of atmospheric air at 1 atmosphere, okay? Then there's another problem, which is called volumetric efficiency, and that has to do with how efficiently the engine manages to suck air in past the valves and into the combustion chamber. And you've got to appreciate that engines are designed to operate over such a wide range of revs, right? From 600 at idle to something like 6,000 at peak power. And that's a major change. And they're more efficient at sucking air in and, getting it out at certain revs and less efficient at others. And they're very volumetrically inefficient at idle. Engines are typically designed to be most volumetrically efficient at about 2,500 revs. That would be engines for road cars anyway, because that's kind of where you're cruising, and it makes sense to be volumetrically efficient at those kinds of revs. Volumetric efficiency is only about 50% at idle typically. That's a ballpark estimate. And that reduces your 200 litres, which have already been constrained by your manifold vacuum and sucking past the throttle, to about 100 litres of air at 1 atmosphere, the stuff we're all breathing right now. And 100 litres of air per minute at 1.225 kilograms for every cubic metre, which is the approximate sort of density of air, the mass density of air. That leads to 7.35 kilograms of air going into the engine per hour when you calculate it all out. So the ideal air-fuel ratio, which you've probably also heard about for gasoline, is 14.7 to 1. That's a mass ratio. So however much air is going in, it's 14.7 times more air by mass than it is the fuel by mass, the gasoline, the petrol, America, Australia, whatever you call it, okay? So the fuel per hour, when you calculate all this out, is 0.5 kilo per hour, all right? That leads to the density of fuels, 0.755 kilograms per litre, or 755 grams per litre. And so that means 1 kilogram of gasoline is 1.32 litres, and we've got 0.5 kilogram going in. That means about 662 mils, based just on the theory of the absolute basics of engine operation at idle and the kind of physical constants, the density of this and that, and the mass, air-fuel ratio, and all of that sort of stuff that you could probably just get across the line using nothing more than basic high school chemistry. So let's just suggest that this is a ballpark estimate for the manifold vacuum. The volumetric efficiency is a ballpark estimate. The idling speed is a ballpark estimate as well. So our sort of confidence interval for 660 odd mils of fuel per hour is probably something like, 560 to 760 mils of fuel per hour, if you take into account the fact that this is going to be slightly different for every engine, this is going to be slightly different for every engine, this is going to be slightly different for every engine, and even the density of air varies with things like the temperature and also the humidity. I guess that has a slight impact as well. So let's think about all of that in the context of real engine operation and sort this out. In that original report I did on this, I got my facts on idling fuel consumption from Argonne National Laboratory. So they are export grade physics facts, I'd suggest. My favourite kind, now that I think about it. Both compact sedans with 2-litre engines each consume about the same amount of fuel at idle, 0.16 and 0.17 US gallons per hour respectively, despite differing fuel types. Argonne National Laboratory found 0.16 gallons per hour for the compact 2-litre petrol engine and 0.17 for a modern 2-litre diesel engine. That's 600 millilitres rounded off. There's a link in the description to this report, which is actually very, very interesting indeed. And I am not cherry-picking these data, I assure you. I looked hard for the words per litre of displacement or statements to this effect in that full report online and elsewhere on Argonne National Laboratory's resources, and these statements, per litre, are simply not there. Retarded pommy video dude who forgets to look at the camera inconveniently, it's so technical, and those nutbag commenters, all with no technical training beyond having been shown once how to use a mouse and a keyboard, appear to be doing their engineering research using nothing more than a Google search snippet. I know Garage Halfwit did that.
So I looked it up. And lo and behold, I typed in 2-litre idle fuel usage, went bang, and then it came up with exactly what he read out.
The more I watch him, the more I absolutely rejoice, because I am not him. If you type in fuel consumption at idle and consult the modern day oracle, Google, here's what you get. The estimated fuel consumption of an idling engine is 0.6 litres per hour per litre of engine displacement. This snippet originates with the Quebecistanis, up there. The frozen frogs of the north. And the problem with using Google as the oracle is that Google doesn't friggin' fact check anything. It just reflects popularity back at you. As in, Google's thought process is this, okay? People searched for X and they seem to like site Y, therefore we will put that right up the top of the search engine results pages in a snippet. Just take Google's friggin' predictive search, this is great. Type in, "is the moon," and see what pops up. Number 1, predictive search related to is the moon. Is the moon a planet? No, it's friggin' not. Please don't breed or vote if you need Google's assistance answering that. Number 2, most commonly searched for term in this domain by ambient humanity, is the moon a star? Please don't breed or vote. Number 3, is the moon made of cheese? Friggin' cheese. If that is you searching, hoping for an answer on this, probably best just to kill yourself. I'm not kidding. So, yes, Your Worship, I respectfully decline to be tried by a jury made up of randomly selected members of society on the grounds that ambient humanity really is that stupid. But that doesn't mean you have to be that dumb, okay? Frankly, one of the most paradoxical aspects of the modern world is that we've never before had access to so much friggin' information. Unfortunately, though, much of it is, what's that word? It's bullshit. And many people, including side-facing video moron, are just not very good at filtering information for veracity before they take it as absolute truth. Happily though, not everyone is in this category. I work as an engine tester, running engines on dynos all day. Idle uses 500 to 600 mils per hour typically, so John is spot on. We actually physically measure the fuel flow going into the engine as well as a billion other parameters. We mainly measure the fuel flow so we can charge whoever the engine belongs to the correct amount for fuel usage. This is dead nuts accurate and undisputed. Please let this idling stop-start bullshit die once and for all. Hear, hear. Engine stop-start is bullshit. It saves you hardly anything because the facts. The inherent controversy here, what I'm calling idlegate henceforth, is the fuel consumption 600 mils per hour per litre of engine capacity at idle, as Google, whining Pom, sideways dude, and the wacky upstairs Quebecistanis claim, or is it a flat 600 mils for a modern 2-litre engine, i.e. not per litre? Argonne National Laboratory in the USA is a globally acknowledged hardcore applied physics research powerhouse specialising in energy, including internal combustion engines. And that organisation dates back to the Manhattan Project. Links in the description. Safe to say, on this, they know their shit. And the particular nerdy applied physics Yoda in charge of idling research at Argonne is a borderline genius named Dr. Linda Gaines. She has a PhD in physics from Columbia University as well as sundry postgraduate physics qualifications. A friggin' PhD in physics. That is the cognitive equivalent of running a 4-minute mile, meaning hardly anyone can do that. By the time you have a PhD in physics, okay, it's quite unlikely that you'd forget the per litre of engine capacity caveat in a statement encapsulating a fundamental claim you make publicly in relation to your work. Personally, right, I only have a bachelor's degree in engineering, and I would be so disappointed if I made an error of that nature, because that's the kind of little slip-up that make bridges fall down, and we engineers are philosophically opposed to that because it just makes us look bad. By the time you have a PhD in friggin' physics, you're basically a cognitive extreme sports superstar. So there's that. And also, having that statement about consumption up on the Argonne website for months upon months and not having one of your peers get right on it and correct you if it is in fact incorrect, well, that's about as likely as a grand alignment of the friggin' planets tomorrow afternoon at tea time. So I'd suggest that the theory and Dr. Gaines's claim line up pretty well, and that seems to suggest the Google Quebecistani search snippet inspiring whining sideways pom retard and others is fundamentally flawed bullshit. But I know that's not going to be enough to appease some of you. Actually, I'd love to do a test on this, but I'd need a friendly car company that was still talking to me and which was prepared to give me a vehicle with a reasonably modern 2-litre engine. And I'd need to plug it into a proprietary friggin' scan tool to get it idling at zero load and get all that data, preferably with the assistance of a highly experienced master technician. And they're not cheap. And I'd probably need to do that inside some super secret restricted engineering friggin' skunk works, which is off limits to journalists and the general public. Okay, let's do this. Hey, yeah, it's me again, right? Look, can I come over to your place with a bunch of camera gear and invade your super secret local tuning facility and kind of, I don't know, lunch off your resources and tie up your master technician for several hours? Would that be okay? Well, in exchange, I'm prepared to offer you... how's absolutely nothing sound? Yes! Well, that's awesome! That's awesome! Well, I'll see you in about 10 seconds. Thanks so much. I love you too. Bye. Hyundai laid on a 2-litre Atmo petrol Kona, plus I got access to Pete Kiourkas, or as I like to think of him, Edward Spannerhands. The basic process is Bluetooth dongle plugs into the onboard diagnostics port and the data gets streamed wirelessly to a tablet running a proprietary app. The engine measures the mass of air flowing in real time so it can decide how much fuel to tip in for efficient combustion. Once we got to normal operating temperature and made sure the air conditioning was off, the idling Kona was drinking 100 milligrams of air per stroke, idling at 640 RPM. Both of which data points come straight from the engine control ECU. Interestingly, with the aircon on, that jumped up to 140 milligrams per stroke at 680 revs. Getting these data was actually dead simple. All we need now to crack this kooky consumption code is the right mathematics hack to get from milligrams of air and strokes to litres of fuel per hour. My work here was clearly done. Milligrams per stroke, okay? How friggin' convenient. So we've got to get from there, from the two things we know, milligrams per stroke and revs per minute. We've got to get from there to the number of mils of fuel that the engine is actually burning per hour. So let's break this down and just think about the air consumption of the engine and make that more digestible. We'll do that with a really neat cognitive hack, which is kind of okay as long as it doesn't make your brain bleed. So stand by, maybe put some pillows around in case you fall down. You don't want to hit your head as well as bleeding internally. So the interesting thing is you've got to start with what you've got, which is milligrams per stroke and revs per minute. And then you've got to get that more usable in some way. So I'm aiming for kilos per hour of air going into the engine, because we can convert that into the amount of fuel going in using the air-fuel ratio. But the interesting thing to realise here is that the units you've got and the units you need, they behave exactly the same as algebra, right? The algebra that you did in like high school. So you can manipulate them the same way, and you've got to use the constants that you have access to and play around with it a little bit in your head so that you can eliminate the bits that you don't want, like milligrams, don't want that, want kilos, and strokes, I don't want that, I want hours. And I don't so much need the revs and the minutes either. I don't want minutes, I want hours, and I don't want revs at all, so I've got to get rid of them. So what constants have we got access to? Where can we put them in the equation, and how can we cancel them out? So you've got to play around with that a bit. But when you do, we know how many milligrams there are in a kilo, and we can flip that. Okay, there's 10 to the minus 6 kilograms per milligram. There's 1 million milligrams in a kilo. Trust me on this if you're not getting it. We know how many minutes there are per hour. That's basic. There's just 60 of those. And we know how many strokes there are for every rev. There's 2, because it's a 4-stroke engine, and that's how this works. And the cool thing about algebra is that if it's up the top and down the bottom, it cancels out, right? So we've got, for example, revs here and revs here, and we've got strokes there and strokes there, and we've got, what else can we get rid of? We've got milligrams there and milligrams there, and then we've got minutes here and we've got minutes there. How lucky are we? Because all that's left is kilograms and hours. So if we know that, we measured it in the Skunk Works, right? And we measured that in the Skunk Works, at the same time. This many milligrams per stroke at this many RPM. That's what we walked away with. And we know that. That's just a constant. And we know that, and that's just a constant. We know that, that's just a constant. You can multiply all this out. 120 over a million equals 1 on 8,333. Trust me on this. So kilos per hour is milligrams per stroke times RPM divided by 8,333. Yes! All of a sudden, we're looking a lot closer to a solution here. Trust me on this. So let's think about the fuel consumption. How do we convert kilos per hour of air to kilos per hour of fuel? We want kilos per hour of fuel. We've got kilos per hour of air, and we know the ideal stoichiometric air-fuel ratio, which we talked about earlier. 14.7, the air-fuel ratio, times 8,333 is 122,500. That's basic. So that just changes to that. And all of a sudden, kilos per hour of fuel just falls out on our lap. It's milligrams per stroke times revs over the big number on the bottom. Yes! Really easy to go from here to the answer that we want, okay? Because petrol, we know that, it's 755 grams per litre. We covered that off earlier. 1 kilo of fuel is 1.32 litres. So you put the 1.32 up the top and you keep the big number from there down the bottom and you get 92,800 on the bottom, all right? So litres per hour of fuel is milligrams per stroke times RPM divided by 92,800. Now, I've got to tell you at this point, okay, this only works for a 4-stroke engine and a 4-cylinder engine. The numbers are different if it's a 2-stroke engine or if it's got a different number of cylinders, and you have to go back to basics and then derive that, because this becomes 3, for example, for a 6-cylinder engine and 4 for an 8-cylinder engine, for example. So there's that. And then if it's a 2-stroke engine, it's double or half. I haven't worked it out, but it's like that. Anyway, this formula only works with the 92,800 for a 4-cylinder, 4-stroke engine. So remember when we were in the Skunk Works, right? We did 2 tests. What we got was the no-load idling test, and then we put the air on and had a look at that as well. So these are the 2 results. Fuel consumption, the formula that we just worked out earlier, milligrams per stroke times revs over that big number there. We've got 100 milligrams per stroke no load, okay, idling at 640 RPM. That's just 3 numbers. 100 times that divided by that equals 0.69 litres per hour, or 690 millilitres per hour. And when you put the air conditioning on, okay, you're idling away, it's a hot day outside, you've got the air on, what difference does that make? Milligrams per stroke went up to 140, and the RPM bumped a bit as well, thanks to the computer, just keeping up with the extra load from the HVAC system, all right? Fuel consumption, therefore, becomes that times that divided by that big number there, and we got just over 1 litre per hour. So the big takeout here, of course, is that fuel consumption is about 50% higher at idle if you're leaving the air conditioning on. It's still not going to cost you a bomb, like 1 litre an hour here in Shitsville. What's that, $1.50? $1.50 an hour, so that you're not sitting in a car that amps itself up in summer to 55 or 60 degrees C. If I had to pay $1.50 to sit in relative comfort, then hey, I guess I'd just spend the big bucks. A couple of minor points before I let you go, okay? We got pretty decent correlation between Argon's statement about 600 millilitres per hour for a 2-litre engine and my beer coaster calculations. Beer coaster calcs and our actual engine test data from the Kona in Hyundai's very own Fat Cave, modelled off this one, clearly, they correlated strongly, I'd suggest, and that was about 15% higher than Argon's findings. The theory suggested 660 mils per hour. The test told us 690, and Argon's advice was 600. And they are all clearly in the same consumption ballpark with a spread of about 15%. So if retarded POM was right and it was 600 mils per litre of displacement per hour, we'd be finding 1.2 litres per hour for the 2-litre, and frankly, we got nothing like that. Obviously, Argon tested one particular engine in one particular car in one particular set of conditions, and we tested a different engine in a different car on a different day in a different friggin' hemisphere. So I can live with 15% variation across those three numbers. The Kona has multi-point injection, and it may be that the engine Argon tested had direct injection. That would give it a more precise set of fuel delivery controls across a wide range of operating conditions, including idle. The Kona in this test was also pretty new, so it might still have some loosening up to do in the internal friction department as it continues to run itself in. And if that's the case, some of the idling load would probably come off over time, reducing the fuel demand at idle and dropping the consumption closer to Argon's test results. Apart from that, I think we've shown pretty clearly here that it's 600 millilitres ballpark for a 2-litre engine idling under no load, and I would expect that to be proportional more or less to the engine displacement, with all other things being equal, like 300 per hour for a 1-litre engine and 900 per hour for a 3-litre engine. So I sincerely hope that the applied mathematics and the window into dimensional analysis for applied physicists in the beer garden did not leave you with blood streaming from both ears. Or if it did, I sincerely hope you've retained sufficient fine motor control to subscribe. Do it now. Because still to come this week, I'll be reviewing the awesome Lexus LC, a total V8 super hyper performance slice and shredding yes car with some very sexy parts down there, I must say. Plus, there's a report on the beer garden basics of stability control to come. Chances are your car has that, and you might as well therefore know how it works. That's all coming up, plus tool time. Yes, Q&A Monday. We might also get hands-on later on and do jacking up your car together with a bunch of jack hacks that you might not have previously considered. So there's that. So jab that subscribe button right now before your vision fades completely to black, and right hook the bell notification so YouTube can put its hand up your skirt into your desktop whenever I post new content. And as reach-arounds go, I always find that most satisfying indeed.